All right, so we've been talking a fair amount about the E2 reaction mechanism. We said the key thing to consider is your beta proton must be anticoplanar to your leaving group. If it's not, we need to do that Newman projection twist or sigma bond rotation in order to get a situation where the beta proton is anticoplanar. In addition, I've shown you that Newman projection trick where when you do that twist and get that beta proton anticoplanar, circle the groups on either side. Those will be cis to one another in your final alkene. So you can use that to determine whether or not you'll get the E or the Z alkene out for a specific E2 reaction. We looked at a few examples involving cyclohexanes where we said that the leaving group, if it's a wedge, means that your beta proton must be a dash. In addition to that, down here we said with chair conformations, it's important to remember that your leaving group must be axial because that's the only conformation that allows for an anticoplanar beta proton. So if there is a question asking about conformations, you may need to draw out the chair structures for each of the cyclohexane conformations. All right, and then down here we said, all right, there are some situations where you even get more than 2 products. So in this situation, we got 3 potential products and we were able to rank them from most to least stable. And then down here, we finished off talking about this problem. So kind of combining cyclohexanes and E2 chemistry. So in the top reaction, we got 2 different products because we had 2 different anticoplanar beta protons. And in the bottom one, we only got 1 product, right? Because we only had 1 anticoplanar beta proton. All right, today what we're going to do is we're going to go and look at this situation. So why is the one on the left more stable? Does anybody remember why? Beyond just saying tri-substituted? Hyperconjugation, right? So we know that this one over here is going to be more stable given the fact that we have more substitution coming off of the alkene. That provides more hyperconjugation, which allows the double bond to be formed more readily. However, depending on the situation, we can actually favor formation of the tri-substituted alkene over the di-substituted, or we can favor the di-substituted over the tri-substituted. So let's do a thought experiment. Let me zoom in a bit. All right, so let's go back and do that example. So the first example we had a methyl group up here. We had our proton here, and then we had an anticoplanar beta proton. I'll show that in red. And then a second one shown in green. And we said we can get 2 different products depending on which of these anticoplanar beta protons we select. So on the bottom one, we can maybe go after this green anticoplanar beta proton and kick off our leaving group. That gives us this product. And on the top, we could have gone after this one to give us this product. And we said that this one is more stable, and this one's going to be less stable. All right, which one is our thermodynamic product? Who remembers talking about thermodynamic products? Remember, Stacy? So how do we define a thermodynamic product? It's really, really easy to overanalyze this because thermodynamics sounds scary. Another way of asking this is, which is more stable? So which one's more stable? Top one. All right, easy enough. I already told you. If you remember, when we talked about thermodynamic products, we said that this has the largest delta G, right? So when we ask ourselves about a thermodynamic product, we're just saying which one gives you the most stable thing, all right? Which is the kinetic product? Or can we tell? All right, so let's go back. How do we define our kinetic product? Do we look at delta G? Activation energy. All right, so let's make a note on that. Which has the largest EA? What do we think? It's a little bit tricky. What's something I've kind of been omitting? If I look up here, this is just some sort of generic base, right? So let's think about our base sizes. If we have a really, really big, bulky base, which proton is going to be easier to grab, the red or the green? You think the green one? Why would a big, bulky base be able to grab the green proton easier than the red proton? It's less crowded, right? So if we have a big base, the activation energy might be smaller for the green proton. So let's write that down. So big base can grab green H easier. Therefore, oh, this should be lowest EA. Holy cow, sorry. I'm sorry, I completely flipped that. Which one has the lowest activation energy? So the green one we said should have the lowest activation energy with a big base. Because a big base can grab that green proton, it's more accessible, it's not crowded. All right, what about a small base? Does a small base really care which proton it's going after? Not really. Small base doesn't care. We'll grab either. However, if you're a small base and you don't really care which one you're going to go after, which one do you think we're going to make? The more stable product or the less stable product? Probably the more stable, right? So the small base doesn't care, we'll grab either. However, it tends to give the more stable alkene. So it's a little bit weird to think about. So let's briefly kind of review thermodynamic versus kinetic product. So let's consider this situation. We said that this hill we have to climb is our activation energy. Sorry, let me change this a little bit. I want to make sure I have enough room. And up here, we could have another situation that looks like this. In the green pathway, the activation energy is smaller. Although you end up with a less stable product. So down here we can fill this in and we can say reaction progress and energy. And let's make a note down here. This can occur with a large, bulky base. It's a little bit weird to think about, right? All right, so let's try to talk about this in more detail. unfortunately, I think I lost my pictures in here. I'll just give a broad overview. It's two old white men. First white man is named Alexander Zaitsev. Old white man. And then the second guy is named August Hofmann. Oh, I'll copy him over later. But for right now, we'll just say another old white man. So these were the two chemists that were exploring this phenomenon, where they noticed that it depended on the size of the base you were using during an E2 reaction, that you could get different products. And so Zaitsev primarily worked with small bases, and he was the one that noticed that you tend to get the more substituted alkene with small bases. Where August Hofmann found something else out, he said that if you use a big base, you get your less substituted alkene. So these two chemists noticed these competing trends, and because of that, these names have stuck. Anytime you get the more substituted alkene, this is referred to as your Zaitsev product. Anytime you get your less substituted alkene, this is called your Hofmann product. Sorry, this looks like an M. This should be two N's. So in this class, we'll be referring to these a fair amount. Anytime I'm talking about a more substituted alkene, I'll commonly refer to it as the Zaitsev product of the E2 reaction. Anytime we're looking at the less substituted alkene, it's the Hofmann product. All right, so let's see an example of this. Okay, so in this example, I've got a bromine, I've got a hydrogen that's anticoplanar. Then on one side, I'll have a tert-butyl group and a methyl group coming off of dashes and wedges. And then over here, I'll have two different methyl groups. All right, let's say that I treat this with hydroxide. My question for you is, will this do SN2 chemistry? Why or why not? Hydroxide's a good nucleophile.
It will, because proton is anticoplanar with the leading group.
Well, let's think about SN2 chemistry instead of E2 right now. Can this do SN2 chemistry?
No.
Why?
Because it's tertiary.
Yeah, if we think about the carbon with the leaving group, that's tertiary. Can we do SN2 chemistry on tertiary carbons? No. So we're not going to do SN2 chemistry, but we know that hydroxide is also a good base. All right? So if we think about beta protons, we've got a few that we can consider, right? So let's consider the beta proton. I've got this one that's a beta proton. Is it anticoplanar? Yeah, absolutely. Do we have any other beta protons? Where else? Yeah, the wedge and the dash. If we think over here, I've got beta protons coming off of each of these positions as well. So really, we've got a variety of different beta protons that we can select from. All of these highlighted protons are beta protons. All right, now what we want to do is we want to say, all right, is this a big or a small base? Small base. Okay, so this is a small base. Which proton do you think we're going to selectively deprotonate? Or do you think we might get a mixture? And if we're getting a mixture, which product do you think is going to be preferred? It's a little bit weird to think about. Should we just try all of them? Let's try all of them. All right, so we've got this small base. I'll do the easy one first. This one hanging out right here. We can take off one of those. If we do that, we're going to get a double bond. We'll have two methyl groups coming off the left-hand carbon, right? We'll have a methyl group here, and then we'll have a tert-butyl group. Does that make sense? All right. So let's try another one. So I'm just going to copy this because I've got the power of the pen. See if this works. Come on. Copy. Paste. All right. So maybe on the second one, instead of grabbing that beta proton, we go after one of our other beta protons. All right. So what I'm going to do is I'm going to say, well, maybe in this situation, I'm going to go after one of these. Does it matter if it's anticoplanar off of that methyl group? No, they're going to spin around. So one of them is always going to be anticoplanar. So let's try to determine what this would look like. All right, so if we do that, that means that we would have a double bond over here and then a methyl group. Then over here, nothing else has really changed. Does that make sense so far? All right, so in this last example, I chose beta protons coming off this methyl group that I've circled in orange. Would it have mattered if I had grabbed one off of the other methyl group? Why not? And what I mean by that is, would it matter if I, let's say, grabbed one of these, clamped down, and kicked off that?
You're going to end up with the same.
Yeah, so if I did the blue arrow pushing, we'd get the exact same product. So you can show it if you want, but it doesn't really matter in this situation. So I'm just going to go ahead and erase those and say it doesn't matter if I did that blue pathway because it would give me the exact same product. So these are the two products that we could theoretically get out for this E2 reaction. All right, which one's more stable? Top one. All right, so this is the more stable product because it is tetrasubstituted, right? Down here, this means that this must be the less stable product. All right, which one's our Zaitsev product, the top or the bottom? Top. More stable product is always going to be our Zaitsev product. This would be our Hofmann product. All right, we could theoretically get both of these because both of them have anticoplanar beta protons. Which one do you think is going to be major, given the fact that we're using a small base? The top one, right? Because up here, we said that Zaitsev said you tend to get the more substituted alkene with the small base. So we can go ahead and we can say that this would be our major product. And this would be my minor product for this reaction. So we would get a mixture. It wouldn't be an even mixture. And what's the relationship between these two products? Are they enantiomers, diastereomers, identical, constitutional isomers? Constitutional isomers, right? So we have different connectivities. So these would be a pair of constitutional isomers that we would get out from this reaction mixture. Does that make sense? Yeah?
How do you know the hydrogen the proton is anticoplanar because I couldn't.
So the question was for this top one?
Yeah.
How do we know that the beta proton is anticoplanar?
Yeah.
Yeah, so that's a good question. In this top one that I've underlined with the green, you can see that the hydrogen's a straight line coming off, And then the bromine's a straight line, implying that they're in the same plane. And then they're pointed in opposite directions, so they're anti. So they're anti, pointing in opposite directions, and then coplanar, meaning residing in the same plane. Yeah?
Well, doesn't that mean the protons on the methyl groups, some of them won't be anticoplanar to the bromine?
Yeah, so if we go back down here and we say, all right, well, what about these methyl group beta protons? Does it really matter which one's anticoplanar? One of them's always going to be anticoplanar in the staggered conformation. So really with the methyl group, it doesn't matter which one you pick because one of them will always be anticoplanar. With the top one, we had to be very careful though because there was only one beta proton and we needed to ensure that it was anticoplanar coming off of that carbon. Does that make sense? All right, so let's try this again. All right, so down here, I'm going to cheat one more time. And this time, I'm going to use a different base. So in this situation, I'm going to use that big, bulky Tert-Butoxide base. Okay, we could do the exact same thing and consider the two potential outcomes. Oops, sorry, the first one we actually had two methyl groups. We had a double bond methyl group and we had a tert-butyl group, right? So this one's now a big bulky base. And then down here, let's do the same thing. I'm going to erase all my other arrows just to speed things up. I'll say, all right, if we've got a big bulky base, again, we have different beta protons we can select. But in this situation, we're going to go after one of these beta protons. Doesn't really matter which one. I'll just pick a different one this time. All right, again, let's go back to our original questions that we did the last time. Which one's more stable, the top or the bottom? Top. We didn't really change the stability here. Which one's going to be our Zaitsev product, the more stable or less stable? More stable. So that didn't change either. This would be our Hofmann product. However, let's think about the big bulky base. Which one's going to be our major product? The Hofmann product. So down here, we would say this would be our major product. This would be our minor product. It's a little bit weird to think about, right? So really the only thing that changed in this situation was which one's major and which one's minor, depending on the size of the base. It's not that you won't get the other one, it's just you'll get less of the other one, depending on the size of the base that you use. So let's make a note. So big bases favor the less substituted Hofmann alkene. Small bases the more substituted Zaitsev alkene. Yep.
So, because we have the big base, wouldn't it be more likely to go with the proton that's anticoplanar to the bromine because the methyl groups are just so big and a lot of chaos going on there?
Yeah, it's an interesting thing to think about. What I want us to do is let's imagine this bottom reaction down here. So let's say you're the Tert-Butoxide, you're floating around in space and you're trying to find protons to pluck off. Is it going to be as easy to grab this proton that's coming off the tertiary carbon? If you're that big bulky base?
It would seem like it would be easier to get that one because there's not as much chaos floating around on that side.
I would argue it'd actually be harder to grab that solitary proton coming off a tertiary carbon because it has to be aligned in that perfect direction. It's got a tert-butyl group around it. It's got two methyl groups next door and another methyl group coming off of it. So it's really, really crowded when you're trying to grab this proton with a big bulky base. If you think about the methyl group protons, they're just kind of pointed out away from everything. It's going to be a lot easier as a big bulky base to grab one of those methyl protons than it would be to grab one of those protons. I know it's a little confusing to think about though, but big bulky bases have a harder time grabbing protons off of highly substituted carbons just because it's more crowded. Yep, great questions.
It doesn't look crowded in the drawing.
Yeah, in a drawing it's kind of hard to always show realistically how crowded things are. The better perspective that you really have a hard time doing with pens and pencils is the electrostatic potential map. So seeing where the electron density is, and the electron density actually will crowd out some reagents from accessing those carbons and protons as readily. Yep. So let's make a note here too. So down here, so a big base has a harder time reaching this proton. All right, so now let's make a list of common bases. So common large bases. All right, so the first one that we've seen is the potassium tert-butoxide. This one's really common. This can be shown in your textbook a few different ways. Sometimes you see it written like this, KO-TBU. Sometimes you see it written like this, TBU-OK. Really all that means is this group over here is the tert-butyl group. So they abbreviate that as lowercase t followed by a BU, but it always has to be in that order. The oxygen's attached to it, and what's potassium doing here? It's just a spectator. All right, does anybody remember any other super big bases besides tert-butoxide? DBU, that was one of our special bases. I don't expect you to memorize the structure of it, but DBU is one of the special ones that gives you that resonance stabilized conjugate acid. What was the other one? DBN. And then there's one other one. The next one that we haven't really seen yet looks like this. It's a nitrogen with two lone pairs, and then a lithium countercation. This is called lithium diisopropyl amide. Most people just call this LDA. The good thing with all of these is these are all big bases, which means they favor Hofmann products. Will any of these do substitution chemistry? What do you think? Are they good nucleophiles? Why? Why are they not good nucleophiles? Because they're big, right? So in this case, the bigness is not only helping us in terms of favoring our Hofmann product, but it's dissuading these from acting as nucleophiles and doing substitution chemistry. So it's a double win if you're aiming for your Hofmann product. All right, let's take a look at common small bases. All right, common small bases for E2. All right, we could do hydroxide. We could do methoxide. All of these could have sodium along with them as a countercation. I'm kind of leaving that out now. We could have ethoxide. We don't want to go all the way up to Tert-Butoxide because that's too bulky. And then the last one that's pretty common is hydride. So down here we could write NaOH as an example. We could have NaOMe. We could have NaOET, that's sodium ethoxide. Or we could have something like NaH. You see how sodium's just a spectator cation for all of these as a positive charge? All right, this one's a little bit more complicated. Can any of these do substitution chemistry? Which ones? Ooh. Why not the last one? It's insoluble, right? So this one's a bad nucleophile. Therefore, it can only do E2 chemistry. These ones can also do SN2 because they're pretty good nucleophiles, right? All right, so it gets confusing. Students are like, well, if that's the case, why did you use hydroxide in the last one? Why didn't we have to worry about substitution again in our last example? So let's go back up and look. So up here, up here, why was I allowed to use hydroxide in this example? Yeah, if we look at the carbon with the leaving group, can we do SN2 on that highlighted carbon? Yeah, because it's tertiary. So sometimes you have to worry about SN2 if it's, let's say, a primary carbon, but if it's tertiary, it's never, ever, ever going to do SN2, so you can get away with using any of those bases. Sometimes students will say, well, if that's the case, if you're doing E2, why don't you just always use H-? Why would you ever use OH-? Hydroxide. Does anybody know why? So I had a student one year and he was just like, this is silly. Why don't we just always use this? It only ever does E2. Why would anybody make their life more difficult by using one of the other ones? It's all about the money, right? Hydride's actually quite expensive to buy. It's a lot cheaper to buy sodium hydroxide, so if you can, it's better to use a cheaper reagent. The other one is, I don't know if I told you this, but hydride is actually pretty nasty to work with. You can't store it in normal containers. Normally when you buy it, it comes in a plastic baggie because it'll react with metal. So we don't want it to react with metal or glass, so they put it in a plastic baggie, and then you have to scoop it out of a plastic baggie when you want to. I remember one time vividly in grad school doing this, where I was scooping out hydride from a plastic baggie, and then I went to go close the baggie, and it shot the powder in my face. It's a good example for why you always, always, always wear safety glasses. Had I not been wearing them, that powder would have been in my eyes. So it's kind of nasty to work with. It's a great base, but typically we only use it if we absolutely need to avoid unwanted SN2 chemistry. All right, does that make sense? All right, there's a few new terms I want to introduce. All right, first one is stereospecific. And then underneath that, we'll compare that to its counterpart, stereoselective. All right, so let's compare the roots here. We've got specific versus selective. What does it mean if you're specific? So think about car shopping, right? Let's say I'm going out and I'm going car shopping and I'm saying I'm being very specific. What does that imply? I'm looking for one type of car, right? What about selective? How does that differ from specific? Open to options, right? So maybe when I'm car shopping, I'm saying I want an SUV. It means I'm being selective. I want an SUV, but there's a lot of other SUVs out there besides just one make and model, right? So let's try to define this in terms of chemistry and not cars. So a stereospecific reaction is a reaction that gives one stereoisomer as a product. A stereoselective reaction is a reaction that gives an unequal mix of stereoisomers. So the main difference is when you're specific, you only get one thing. When you're selective, you don't just get one thing. You're open to a lot of things, but you prefer one thing over the other, right? So for example, my car shopping analogy, I prefer an SUV, but yeah, crossover would be fine as long as I can get to where I need to go. All right, so those are two new terms. There's one last one, though. Regioselective. All right, in this case, again, the root is selective. What does that imply? Are we getting one thing or multiple things? Multiple things. And in this case, it's not going to be stereoisomers. It's going to be regioisomers. What do we call it if things are given, or you get a mixture of products where they have different connectivities but the same molecular formula? Constitutional isomers. So it's a reaction that gives an unequal mix of constitutional isomers. So all three of these get thrown around a lot in chemistry, and I've seen a lot of students not really know what they mean. But as long as you understand the difference between specific and selective, that gets you halfway there. And then if you think about stereoisomers, what two things can be qualified as stereoisomers? Enantiomers and diastereomers. Regioisomers are always going to be constitutional isomers, so you can narrow it down. Some students will say, well, what about regiospecific reactions? What would that be? It means you just get one product, which in this case actually falls under the stereospecific reaction because you're just getting one thing. So normally people don't use the term regiospecific. All right, let's go back up. Let's look at this example. So in this example, we've got a mixture of two different products, major and minor. Do you think this is going to be stereospecific, stereoselective, or regioselective? Regioselective. So up here, this would be a regioselective reaction. Got a mix of constitutional isomers. All right, so that makes sense. Let's take a few other examples. All right, I'm going to give you two examples down here, and I want you to help me figure these out. Let's say that I have this reaction. And I'll give you a hint that this is SN2 versus This one. Actually, sorry, I'm making this up on the fly, so I'm going to add wedges and dashes here. All right, so for these, let's determine what product or products we'll get out of these. Who thinks they got the first one? So the first one's pretty straightforward. If it's SN2, we're going to attack this carbon, kick off our leaving group. Will we get more than one product? No. So would this reaction be stereoselective, stereospecific, or regioselective? Okay, so this would be stereospecific. All right, let's think about the next one. First step would be loss of our leaving group down here. So we could go ahead and we could say, all right, if that happens, what we're going to do is we're going to have kind of this trigonal planar transition state where we've got this empty p orbital. And water, we said, can attack from either face here. So let's draw both of these, where we've got water on the top face, right? And then we could have water on the bottom face, where it's attacked. And then we can get to our final product by removing one of these protons. I'm just going to cheat and show this as minus H plus to simplify things. And we would get two different products. All right, so in this top example, we got one product. In the bottom one, we got two. Are we going to get a perfect 50-50 mixture of these two products for SN1? What do you think? I'm not even asking if it's which one's going to be major or minor, but will we get a perfect 50-50 mix? Why not? If we think about the bromine falling off, this bromine is going to be floating around in space, right? In this case, it kind of flew off, I guess, more or less the top half. So if we think about that, is the top face going to be major? No. If we think about this, the bromine's going to have a harder time, or the bromine's going to block that top face attack a little bit. So in the example shown, this would be minor. This would be major, just by a little bit, not by a lot. So would this reaction be regioselective? No, what would it be? Stereoselective. So that's one thing to pay attention to. Oftentimes with SN2 reactions, it's always going to be stereospecific, but with SN1, depending on whether or not you're creating a new stereoisomer, it can be stereoselective or stereospecific. It just kind of depends. In this example, we're getting a mix of stereoisomers, so it would be stereoselective. Yeah?
I'm just wondering, there's the one we had, and the leaving group match, right?
Mm-hmm.
What is the other methyl group have?
The other methyl group?
There's like the methyl group on one side.
You're talking about these?
No, on the other side. Yep.
Right here? Oh, it's just right here. Right? So there's a tert-butyl group on each of these.
Okay.
I just tried to show it kind of flattened out because we know it will go through a trigonal planar transition state. So it's still the same molecule. It's just showing kind of flattened out as trigonal planar. Yep. All right. So I know a lot of this is super confusing. Before we leave, I just wanted to say I've got a supplemental video on E2 chemistry. I didn't really go into a lot of the nitty-gritty detail today during lecture because I found it's just too much to absorb all at once. So I have a supplemental video online. If you'd like to watch it, you can. The notes will also be in OneNote. And then tomorrow what we'll do is we're going to dedicate the day to E2 practice. So come in ready to do E2 practice tomorrow in class. And then we'll do E1 chemistry the following day.